The
I
floor
think you're
is
seeing my
yours.
screen there, are you?
Yes.
I'm trying to figure out how to get this to be the full screen.
No, that's perfect.
Is it? Okay. I
Yep.
can't see all of it, but maybe you can. So good morning, yes, and welcome from Ireland, southwest coast of Ireland, which has similar winds to where you are in Denmark, I'm sure, because we look out on the Atlantic. We originally developed wind turbines, but we quickly moved into just developing controllers. Just a brief potted history of the typical domestic installation. You had a turbine connected to a via safety brake, a short circuit brake, to a wind interface which provided rectification, and this went into wind inverters, which typically were made by either SMA or by Jinlong or by Power One in Italy. And the early models only worked on the basis of having a power curve based on voltage to control the conversion. Obviously, as the turbine speeds up, you need to export more power to the grid, and as it slows down, you need to rapidly ramp that down. If you don't do it rapidly, particularly as the power decreases, then the inverter might be trying to pull 6 kilowatts from a turbine that's only capable of delivering 2. It'll immediately stall the turbine and increase the. So more recently, a frequency-based power curve, which more accurately reflects the speed of the turbine and the amount of power available. So based on the frequency of the AC, the wild AC coming from the turbine, the inverter converted that amount of power and in turn applied that as torque to the shaft of the generator. There's a wind version of the Trio, of the Trio solar inverter, which was also adopted to work with a special controller that took the frequency of the turbine and converted it into a frequency that it fed to the inverter. So the inverter had a power curve which was simply 50 hertz was 0 watts and 150 hertz was 30 kilowatts, and in between was a sliding scale. But the logic for the power curve was in the interface this time, not in the inverter. Now as time went on, the companies making wind inverters found that their market was primarily solar, and they gradually decreased their support for wind because as solar panels fell in price and wind turbines remained constant at a constant price, solar became a more economical way for most domestic houses to produce their own electricity. But so I forget what year this was. It was about 6 years ago. But suddenly SMA, FEMA or ABB, and Jinlong all stopped making wind versions of their inverters, and the market was in some difficulty to find an alternative that was reliable. In conjunction with ABB, who ran Power One at the time, we developed a controller to operate with their solar version of their inverters. So the power curve now is stored inside a controller made by us, and through Modbus we disable the MPPT tracking in the inverter, and through Modbus we told the inverter how much power to convert. When we go through that sequence of reading the voltage or the frequency of the turbine, looking at the power table, and sending a message to the inverter times per second, so that the inverter very quickly and rapidly is kept pulling the correct amount of torque from the shaft of the generator and converting that to electricity. We also produced a smaller unit, which includes a rectifier for the 3 kilowatt to 10 kilowatt sort of size of turbines, working into the new FEMA model of inverter, the Uno DM for the single phase and Trio for 3-phase. So the first unit we had is a small power curve controller, which is a little PLC that we make ourselves. And it stores the power curve, which is fed into it by a USB cable from a laptop computer using our own software. It can either read the turbine AC frequency, the wild AC frequency, which is put into these connectors here, or it can read the DC voltage of the turbine, which is taken from the rectifier here. And then it manages the inverter via Modbus, so you have connections here to the Modbus of the inverter. It also has a micro SD card located up here, and it records the revs of the turbine as frequency, the turbine voltage, and the inverter parameters. So in a typical setup where a company had their own rectifier and dump load, they would use this small PLC to control the inverters and to manage the power curve. Okay. So then we developed a rectifier controller because obviously a lot of wind turbine manufacturers didn't make their own rectifiers and dump loads. So the rectifier takes wild AC and converts it to DC and provides smoothing capacitors. And we have various options of smoothing capacitors depending on the number of pole pairs in the generator and the frequency at which it's running. Obviously, a higher frequency generator needs less capacitance than a one with very few poles and its lower RPM. So this rectifier controller also stores the power curve and has a microprocessor that manages the power curve control of the inverter. So again, we override the MPPT tracking in a solar inverter, and based on either frequency or voltage, we control the power curve via Modbus. We also have a variable dump load, which can be either done by pulse width modulation, so it's completely a variable load. So it doesn't cut in with a bang of 530 volts like the old dump loads used to do. Or if you prefer the old hysteresis system, you can do that. But the hysteresis system used to bring in a dump load at 530 volts and switch it off at 430 volts DC. And that causes a lot of ripple on the DC coming into the inverter. We also provide a DC dump load. The board has a backup power logic that simply works a DC dump load speeding during a power cut. So this, it's got inputs from the turbine over on the right hand side and outputs to the DC to the inverter and the dump load on the left hand side. It also has an anemometer input for data logging and for turbine control. We speak about that a little bit more later on. And it includes a general purpose relay, which can be triggered by either turbine over voltage, turbine over speed, wind speed running too high, and it can operate an external brake system. Sometimes that'll be a linear actuator to change the pitch of the blades. Sometimes it might be a three-phased wild AC dump load or any other. I've seen people use it for to operate a disc brake or release a disc. We're also working with hydro and trying to develop a hydro power curve optimization because hydro also can't work with standard, in many cases, it can't work with standard MPPT tracking in an inverter. The controller also has a Modbus for external monitoring, so it has a micro SD card inside it that data logs once per second, but it can also provide that information via Modbus, and it stores or transmits the RPM of the turbine voltage, the inverter status, including the AC and DC voltage and current, and its fault state. It can also, if an is connected, it can record the wind speed. And quite importantly, it can also detect phase loss of the turbine. That's particularly important if you have a turbine where you're using a frequency-based power curve. If you have a voltage-based power curve and you lose a phase, the voltage will fall and the generator will generally stop, the inverter will generally stop pulling power because the voltage will have fallen by so much. It will have fallen off the power curve, but the frequency might remain the same depending which phase you lost. If you lost the phase that you're measuring, the frequency will fall off and the inverter will stop pulling power. But if you lose frequency that you're not measuring from two phases that you're not measuring from, the turbine will then continue to be loaded by the inverter, and it will cause a lot of vibration and could do damage. So phase loss detection is quite an important feature. It is possible to use the anemometer logging to improve power curves in a very, we've seen some earlier talks about developing power curve and maximizing your power curve. You're optimizing the power curve table to maximize the power harvested from the turbine at various speeds. I have to say that in my experience, a lot of turbine manufacturers haven't done this work, particularly in the Far East, and turbines come in with power curves that are wildly off the mark. Because we record the wind speed alongside the RPM of the turbine and the power produced by the inverter. It enables manufacturers or turbine developers to optimize their power curves in a very crude way, but it's very simple and straightforward. So generally speaking, because they're both on the same time clock, it's quite convenient to have the power conversion and the wind speed data on the same timeline. But I must say that in my experience, there's about 1.5 to 2 second delay between wind speed increasing, being recorded by a cup anemometer, and the RPM of the turbine increasing and more power being available. And so you have to, in a spreadsheet, you have to offset it by 1 to 2 seconds to get them back into line again. But a very simple procedure is to use an experimental power curve or the power curve that you're given initially, data log across, then try raising the power curve by 10% across the board and see does that improve or reduce the power production at each wind speed. And if it improves it at a high wind speed, you might take another 10% there. If it made it worse at lower speed, you might reduce it by 5% there and bring it back towards where you were. And as I say, rinse and repeat. If you repeat that procedure a number of times, you can optimize the power production from your turbine for various wind speeds. Another thing because we have a pulse width modulated dump load control, on some sites where people want to do very rough testing of an early prototype, they may not have grid available on the site. And using the pulse width modulation on the dump load, you can actually imitate the power curve that you would use for a turbine. So in Excel, for example, if you change the figures here, so if you started at 50 volts and ended at 400 volts and have a 20 ohm resistor, you change the power curve that you're applying to the turbine, and changing those three figures in those three yellow boxes, you can get very close to an approximation of what an inverter would do with a normal power curve based on the power harvested being proportional to the square of the voltage, which quite often it approximates to. It would give a very rough way of assessing that a turbine actually works before you go to the trouble of putting a grid in place and inverters and so on. We work with ABB and FEMA. ABB, this company has been passed from Power One to ABB to FEMA. And the reason we use these inverters is because they can respond very fast to Modbus commands, much faster than any other inverter that we've seen on the market. If anybody knows an inverter that does it faster, I'd be interested to know about it. But we can basically change the power setting from the controller and tell the inverter to change its power harvesting. We can do that 30 times per second. Whereas most solar inverters take about 2 seconds to respond to the Modbus command. We do use other slower Modbus command inverters for hydro and for CHP. Now, in the last year, I don't think I'm out of order to say that the FEMA company experienced financial difficulties in Q1 to Q3 of this year, and to some extent in Q4 of last year. And this resulted in the company was basically in what is the equivalent, as Americans would know, of the Chapter 11 procedure, where it's managing its creditors. But the company has now been taken over by McLaren and Grey Bull of the Formula One motoring fame. And they're now well funded to ensure procurement of components and continue production. So the company is back in production. But we have had a rough year of it with very slow deliveries and long lead times. Lead time on some products being 8 months to a year. New inverter products are also now in development, so we're quite optimistic with the company going forward that it has the backing of McLaren, Big Grey Bull, and it has very good engineering, so we're quite satisfied that it will work as a product range. For off-grid applications, rather than putting the turbine directly into the battery, in an awful lot of older off-grid applications, the turbine was put into a battery, which means that the MPPT tracking for the turbine was not observed. Turbine spun freely until it got to battery voltage, and then it was locked to that battery voltage and working basically the same way that an asynchronous turbine would work. It was fixed to a fixed speed almost. we maintain the same system as a grid tie turbine with the normal controller, wind interface, and the grid tie inverter working into the AC hot out of Victron or other inverter chargers. That requires, when the Victron changes its frequency, it requires the turbine, this inverter here, to respond to frequency shifting. We can do that with our controller. We can either frequency shift, control the inverter output by the frequency shift on the inverter. On the inverter, we can also read the frequency of the grid through Modbus and respond to it by reducing the power converted by the inverter. And to keep the turbine under the same load, we can increase the dump load. So when the frequency goes above 52 Hertz from the grid, it's detected by the inverter, comes to Modbus into our controller. The controller responds by increasing the dump load and decreasing the power converted through the inverter. And right up to the point where it reaches 53 Hertz, and then it switches off the inverter and all the power from the turbine goes into the dump load. And that, of course, can also work over a three-phase system with 3 inverter chargers, working into the AC hot out of the 3 inverter chargers. Okay, just these are some of the screens on our controller software. The options that you have available. You have the histories, the pulse width modulated dump load. In this case, the dump load would start at 400 volts with 0 power, pulling 100% of the load at 500 volts. So at the dump load, you might have a power curve that's operating up to, we say, 360 volts. And at 400 volts, the dump load would gradually come in. At 500 volts, the dump load would be applied 100%. We have a box here for the ohms of the dump load because we also are able to data log the power going through the dump load and see how much power is going through the dump load over a period of time and how many kilowatts it's producing, how many kilowatt hours is produced in the last few seconds. And you can also take it that if you want to start with a bump, you can start that you start with 80 out of 255 of a dump load setting. So the dump load here in this case, because this is set to 80, will come on at 1/3 of full load and then will gradually increase as it goes between 400 and 500 volts. Now, when the grid is lost, this circuit doesn't work because it requires the grid to power it. But we have a backup power supply that's able to work a smaller processor that keeps the dump load operating in hysteresis, so it comes on at 530 volts and off at 430, and those settings can be set. For the for the overvoltage, to operate the relay that would control a permanent dump load, you've got overvoltage and overvoltage timeout. So if it goes above 530 volts, you might operate the dump load or the blades or whatever it is that you want to do to break your turbine, and it would cut out after a certain period below of time after it's fallen back below this voltage. Similarly, if the turbine overspeeds 20 above, in this case above 28 Hertz for 25 seconds or above 30 Hertz for 2 seconds, then the relay will apply and it'll time out after a certain period of time when the frequency has fallen below the level. The same things for wind speed. If the anemometer meters per second, or the dump load can come on until it goes below 15 meters per second, and you've got an anemometer timeout and an anemometer multiplier. This is to calibrate for whatever brand of anemometer you're using. And you have the normal power curve input that you can put in whatever power curve you're using for your turbine. And this is all the information that's monitored. You can see the time, the state of the auxiliary relay, the wind speed, peak wind speed might be the peak wind speed in the last 10 seconds, the inverter power currently, and so on, the turbine frequency, the turbine voltage. Obviously the frequency isn't connected here, so it's not reading Hertz, but it is reading turbine voltage, 320 volts, which interestingly is also what the inverter sees the DC voltage as being. Okay. And then there's advanced options for setting the grid. This is power limiting when the grid frequency goes above 50.3 hertz or 51.5 hertz. This is to control in an off-grid situation, but there's all sorts of advanced menu settings there that are available. Okay, now that's me out of time. I don't know if I'm early or late finishing there. Anybody got any questions?
Thank you very much. Any question from the audience?